So today we're going to violate the most sacred rule at Caltech, which is that all classes shall be canceled on senior ditch day. That since the seniors and anyone else who wants to go participate in ditch day have the opportunity to see the lecture on the web, and since we have a guest lecturer who is well known to be a superb lecturer and just come down from JPL to give a lecture, I thought we would go ahead. So we have John Armstrong back today. I introduced him before when he talked about gravitational wave detection by Doppler tracking of spacecraft, which he has worked on for many years, and he and his collaborators at JPL are taking the lead on data analysis issues for LISA, having had a lot of experience with the Doppler tracking area. So, in fact, the most important developments to underlie data analysis are due to Armstrong and his collaborators, Frank Estabrook and Massimo Tinto. And John is going to tell us today about issues in LISA data system and data analysis and data channels.
Thank you, Kip.
Now he's prepared 1 hour of lecture, so the challenge is asking enough questions that lasts an hour and a half.
Okay.
No, Sterl's not going to talk today.
Okay, so I'm going to talk today about one aspect of signal processing for LISA, and that is the what my colleagues Frank Estabrook and Massimo Tinto and I have called time delay interferometry. I'm going to start this lecture in the obligatory way by reminding you of what LISA is and what the main noise sources are, and why it is that conventional cancellation schemes won't work for LISA. Then I'm going to talk a little bit about time delay interferometry, which really starts from viewing LISA in a symmetric way as 6 one-way links rather than having a preferred quarter mass and 2 end masses as in the conventional Michelson. And I'm going to, I hope, motivate the use of transfer functions for both the gravity wave signal and for the noises to the time delay interferometry observables to show how you can calculate the sensitivity. As a consequence of that, I guess I'll derive basis functions for ways that one can form in principle an infinite number of ways to cancel the leading noise sources. And the applications I'm going to talk about today, really I'm going to talk only in detail about the first one, which is the LISA sensitivity to periodic waves, but and only allude to other applications. And at the very end, I'm going to talk a little bit about practical problems and things that I think where there's going to be some things that need to be worked on. Here is a list of references which will be on the handout in the web. For LISA configuration for its orbits and for the noise sources, the pre-phase A report is the sort of the Bible. Bill Faulkner and colleagues have written a very nice paper on the orbits. And of course, you've had lectures by Bill, Bob Spiro, Bonnie Shoemaker, and they're available on the web too. These are the papers that Frank Estabrook, Massimo Tinto, and I have written, and I particularly commend this Jaguar talk that Massimo did a couple of months ago. It's on the web along with a video and has some nice animations of how time delay interferometry works. There's also going to be a tome, it's 42 pages, describing time delay interferometry in nitpicking detail, which will be posted on this website after we get the JPL clearances. But that'll still be another week away or so, I think. Okay, so you're all aware that LISA is a NASA-ESA collaboration, searching for gravitational waves, actually doing more than searching, will detect gravity waves in the low frequency band. The expected sensitivity is about 10 to the minus 23 for a periodic source if you're allowed to integrate for a year. It's 3 spacecraft with 6 lasers. Each laser is on an optical bench. 3 USOs, 6 proof masses. A USO is an ultra-stable oscillator. It's an oscillator that is, despite its name, not all that stable. And I'll talk a little bit. I'll talk a little bit about what the problems are with the ultra-stable oscillator a little later. Thank you, Kip. LISA is almost an equilateral triangle, but this is a part of the problem is that there will be time varying arms, and the arms are not equal in their time varying. And of course, laser signals are exchanged between spacecraft pairs. And the true evidence that LISA is a collaboration is the multiplicity of different ways of characterizing the noise sources. For example, it's either hertz squared per hertz, meters per root hertz, or meters per second squared per root hertz. And so one of my contributions to science here has been to convert these various noise sources, which are one-sided, to a consistent set of spectra, which are spectra of delta F over F per hertz. So they're one-sided spectra. You integrate from 0 to infinity to get the variance, and that is why they're per hertz and not per root hertz. And you get the variance when you get that. So I guess the point to watch here is that the raw and laser noise is at 10 to the minus 26 per hertz, and that is to be compared, for example, with proof mass noise that, well, it depends on the frequency, that is orders of magnitude lower.
This ignores the stochastic forces noise. Is this just optical? Right? This is the first. Okay, the first one, the raw laser noise, is the intrinsic instability of the laser. Oh, I'm sorry. These are the various contributions. Excuse me.
Yeah. Okay. And two of these can be made to cancel, or at least cancel acceptably. And the two that contribute finally to the sensitivity are the optical path noise and the proof mass noise, which are inevitable. Okay. So the pretty picture. This is taken.
You'll define the y variable with your.
Y is delta F over F. It's the change in frequency divided by the center frequency. It's favored by the frequency and timing community because the so-called Allen deviation of delta F over F is a characteristic of how good an oscillator is. And this in my opinion, is a nice way to in a consistent way, discuss the noises of a bunch of apparently disparate noise sources. And so that's why all of what I'm talking about today, I'll convert into that mode.
So can you tell us how that's related to H?
I will show you, right.
You'll show how those SYs are derived from
I'm sorry, Brian?
You'll show how those SYs are derived from the nominal noise values that have units?
I can tell you there's no magic here. What for example, consider optical path noise characterized by 20, I guess it's picometers per root hertz. So you square that to get something that has what I would regard as a proper power spectrum. So it's variance per hertz, meters squared per hertz. And to get velocity, you use the derivative theorem for Fourier transforms to get that to a velocity. And then you divide by c squared to get delta F over F. So it's just the derivative theorem for Fourier transforms, but I think it's nice to have them all in the same units. Okay, I remind you that LISA is going to trail Earth orbit by about 20 degrees. It's an approximately equilateral triangle. These are taken from the LISA viewgraph package on the LISA website, which is one of the references that I gave at the beginning. And I remind you again, you've seen this diagram a zillion times, but the triangle sort of, because of the inclinations of the orbits of the three, appears to rotate as it goes around 1 year. And this is not formation flying in the sense that NASA uses this word, at least. We are not trying to control the distances. In fact, at least my understanding of the current baseline is we're not trying to control the distances. So we're just letting these things to be on free Keplerian orbits, and as a consequence of the slight ellipticities, you get slightly varying arm lengths, and the arm length variation is of order 2%. And that's shown in this diagram that I took from Bo Faulkner's presentation a couple of weeks ago. Was plotted horizontally as time into the mission, starting at 0 for 5 years. These are the arm lengths on the vertical axis in the upper panel, and the rate of change of the arm lengths in the second panel down. So here to here is 1%. So the variability is of order a couple percent over time scales of order 6 months, and the peak to peak maximum rates are about 10 meters per second. And this is going to be important later on. The rates are going to be important later on because if you can't have constant center frequencies of the lasers, or if you have Doppler shifts, then there's a unfortunate complication which I think is probably inevitable in the LISA design. We'll talk a little bit about that in terms of the time delay interferometry and what it might mean. Okay, so why do we care about any alternative to conventional Michelson interferometry? And this is where I would really recommend you look at the video that Massimo Tinto has on the Jaguar website, because he has a nice little animation showing how these things cancel. But the basic idea is, of course, one that you've heard before, that an equal arm interferometer, laser noise, laser power, which is injected into the laser, is split and goes down 2 equal arms, comes back. Each arm sees exactly the same time delay. So when the signal is recombined, the laser is Tom in mode and it cancels exactly. So you can have a terrible laser, and to the extent that you can control the arm lengths, it doesn't matter. However, as I mentioned, because of LISA's orbital dynamics, you can't have equal arms for LISA. You're going to inevitably have non-equal arms and also time variable arms. You can estimate what the error would be if you took the LISA nominal parameters, which are slightly different arms, say 1 or 2% difference, the LISA nominal noise source, and you just recombined the data, pretending like the arms were equal, but they weren't, and you can get an estimate then of how much cancellation you get. You get a lot of cancellation, but you don't get enough. You still fail by 3 or 4 orders of magnitude in terms of trying to reach the LISA design sensitivity. So just differencing the arms won't do it.
So what is C here?
There's an unfortunate convention here. C stands for laser noise. You might think it stands for clock noise, and that's unfortunate because USOs are clocks. And the short background for this is that this is like for Doppler tracking, like the frequency and timing system. So that's why it appears as a C. So you'll see some symbols which I hope to do a better job of defining later on. But C stands for the laser noise. Okay, so Massimo Tinto had a very nice idea a few years ago. He considered the situation where you had a one-bounce Michelson interferometer. So you've got mirrors here, unequal arm. And I believe it's true that the first idea of separating the arms and dealing with them independently is due to Pete Bender and Fowler, I think, in a different context. But Massimo's idea is this. It comes down here, it bounces off, and you separately read out the difference in phase, say, or frequency between the laser light you're transmitting now and what's returned to you separately in arm 1 and arm 2. And if you just take those data, and I have here called them phase, and form this linear combination. So you take the process observed in arm 1 and you offset it by the time delay in arm 2 and subtract the process in arm 1, and then difference that from the symmetric version in the other arm, and this cancels the laser noise exactly. And I think this is a very nice insight that he had, because it's in a time domain. It's extremely simple, much simpler to implement than other ideas, I think, and I just think it's neat. You, of course, have to know the arm lengths, and it turns out that for nominal LISA noise sources, the noise spectra and distances and arm length mismatches, you have to know the arm lengths to about 30 meters, which is easy, so it's not a problem. And as I mentioned, there's a discussion of this on the web and also in this paper. This diagram just shows you the magnitude of the problem. What's plotted here is the power spectrum of the laser noise in units of variance per hertz, and delta F over F, so it's dimensionless per hertz, as a function of log of Fourier frequency this direction. So here's a millihertz right here. This is sort of the nominal laser, and this is the shot noise down here, and it would be really good to cancel the laser down to the shot noise. And so this is a simulation showing that the time domain cancellation scheme does a nice job of doing that. It modulates the spectrum as it should, as it's expected to, but it does the right thing. But the really frightening thing here is you need about 140 dB of suppression in common mode to get down to where you need to be, and that's a very big number. So following up on that idea, you can imagine other ways to do it other than the unequal arm Michelson. And the idea, the main idea, the whole point of what I'm trying to get across in this talk is really captured here, I think, is that if you think about LISA in a symmetrical way, so that no one spacecraft is preferred, and just imagine one-way beams that are transmitted between optical benches on one spacecraft to an optical bench on a different spacecraft, and I'll show you how you have to bounce off the proof mass too. You can then use linear systems ideas to evaluate the transfer function of the signal and the noises to these one-way lengths, and how to combine off time shift and add these signals in order to cancel the main noise sources. And the main noise sources here are the laser phase noise, which is the dominant one, but a non-trivial noise source is the non-inertial motion of the optical bench, and that cancels also to a good approximation. And applications, I'm going to talk today about applications. The one I'm going to talk about principally is the sensitivity calculation. So that's really all I'm going to talk about today. So here's the picture, the symmetrical picture. I imagine that well, when I occasionally drop into the word we imagine, this is not meant to be the royal we. When I say we, I almost certainly mean Massimo Tinto, Frank Estabrook, and me. So that's what I mean. Anyway, we imagine that there's a point O, and equidistant from this point O, script L distance, are 3 spacecraft, 1, 2, and 3. Each spacecraft has 2 optical benches. Spacecraft 1 has optical bench 1 and 1 star, 3 has 3 and 3 star, and so forth. There are unit vectors which connect 1 and 3, as indicated here, going around this triangle. And there are, not shown here, but there are vectors which I will later on call K, which locate these 3 points with respect to O. So in the plane of LISA, there are these 3 vectors K which locate the points, and then these unit vectors. And the arm lengths don't have to be equal, and the notation is that L1 is opposite proof mass 1, L2 is opposite proof mass, is opposite spacecraft 2, and so forth. If you consider just this vertex, here's a diagram which is adapted from a paper by Michael Petersheim, and I think it also appears in the pre-phase A document. And this is intended to show the 2 optical benches on spacecraft 1. So here is optical bench 1, here's optical bench 1 star. It's a little hard to see, perhaps, well, I guess it's okay. We have V1 star and V1. And inside these optical benches are proof masses. Bonnie has talked to you about a lot of the very difficult problems associated with the proof masses, but I'm going to assume it all is well and just locate these proof masses inside the optical bench. On each optical bench are on each optical bench is a laser having a random process C1 or C1 star, depending upon which one it is, as a function of time. And there are various beam splitters and mirrors which route the signal around the optical bench. So if you consider just optical bench 1 for a second, laser 1, C1, bounces the signal off of a couple of mirrors and then goes straight off to spacecraft number 2. So the signal that leaves for the other spacecraft does not see the proof mass, it just goes. The inbound signal from spacecraft 2, however, goes through this beam splitter, bounces once off the proof mass, back up to the beam splitter, and comes over here and is mixed with the local oscillator, the laser C1, and that forms a time series of delta F over F. Frequency is a function of time, Doppler shift is a function of time, which is called, in this case, Y31, and that's a slightly unfortunate notation. The subscripts here mean, so Y31 means you're on spacecraft 1, but you're receiving from spacecraft 2, unfortunately. So, and there's a story, as you might guess, but anyway, the point is that it's too late to change now. So,
I actually think of it as you're on spacecraft 1, looking at the signal that came down Arm 3. The notation makes sense.
Shane, very good. Thank you. That's not how it arose, but thank you very much. That's good. Because it's opposite L3. Yeah, so that's very good. Maybe we can adopt that as a cover story. That sounds good. Okay, so you get this measure of the Doppler shift, and in addition, on this optical bench, you get another signal, and that arises from the opposite optical bench laser bouncing a signal off the back of this proof mass, the other proof mass, through this beam splitter, through probably a fiber, over here and then mixed with C1. So you get a metrology measurement of the relative velocity. I'll show you how I'll write some equations down in a minute, but you get some metrology measurements across the back between these two optical benches, and you get some long arm measurements over here. This bouncing off the back is due, I think, independently to Ron Hellings and Peter Bender. I was not in the room when this happened, but it's a tremendous innovation, this idea, because that allows you to cancel things. Having that signal is really important. It was really nice thought. And symmetrically on the other side, it's communicating to spacecraft 3.
So the Z31 is still at fractional frequency.
All of these are fractional frequency fluctuations, right? And
is the output photodiode? What does it actually read in some sense?
Right.
Fractional frequency fluctuations, so you have to do some data processing.
No, what you get presumably is a set of fringes across the photodiode, and then you have to count the zero crossings of the fringes, or some number, count the fringes as they go by per unit time.
This is done in the hardware?
And you can do this in hardware.
That's not your only method, being a fake leader, but that's one possible reason.
Yeah, there may be more subtle ways. Now, everything I'm talking about here is in the approximation that the arms are unequal, the center frequencies are the same of the lasers, and there's no Doppler right now. And I'll talk later on about the complications that arise when those things are not true. But anyway, you get then 12 signals, 4 from each vertex, the 2 Ys and the 2 Zs. So the long signals look like this, the 6 Ys look like this. Now, I've already mentioned about the interaction, the notation I mentioned, everything's equidistant from O. There are some values mu sub I, which are the wave vector of the gravity wave dotted into the p sub I. And the p sub i's, I'm sorry to remind you brutally, are the vectors from O locating the 3 spacecraft. And everything that I'm going to show you, you can generate additional equations by cyclical permutation of the indices. So you just take index 1 goes to index 2, goes to index 3, goes to 1, and then you'll generate the other equations you need. The gravity wave response is the 2-pulse response. This is I think, must be highly analogous to the pulsar timing problem that Kip gave as an exercise. So Hugo Wahlquist formulated it this way, and I think very elegantly. The gravity wave signal observed, for example, on the Y21, which is received at 1 from spacecraft 3 along arm 2. Is given by a coefficient which depends on the geometry. The mu's are k dot pi, and then the difference of two events which happen when the gravity wave hits the transmitter and hits the receiver. And these scalar functions are constructed from the tensor H by dotting on both sides the unit vectors connecting the two test masses, and normalized in this way. So this is I think a very clear paper. I recommend it as an interesting way of thinking about.
So they have derived something.
Right. Yeah. Okay. So 2-pulse response, and you can then, just to bore you with a detail, the spacecraft Doppler tracking thing, which is near and dear to my heart, can be easily built up by, and I think that was maybe an assignment too, or a possible problem, built up from appropriate enforcement of a transponding condition on the one spacecraft. Then you get the 3-pulse response. So 2 pulses if you've got free test mass, free oscillators on each side. As the gravity wave hits one, hits the other. 3 pulse if you enforce a transponding condition at 1, which is the spacecraft Doppler tracking case. Okay, there's a 4-pulse response if you have a equal arm Michelson, and I'm going to show you that in general the unequal arm Michelson is an 8-pulse response. So it gets more complicated as time goes on. Okay, in addition to the signal responses, there are noises. The one noise is the difference between the laser noise at the distant spacecraft that's being transmitted to you and your local laser noise. So that's just the difference between those two noises. This is a huge effect because these numbers are big. There's shot noise, which I think you've all been Bill Faulkner at least has certainly talked about that. Inevitable noise due to the fact you don't have infinite signal-to-noise ratio. Because of the way the light is routed around inside the optical bench proof mass assemblies, there is a contribution to the observed little Doppler frequencies due to the non-inertial motions of the optical benches and of the proof mass. And by just tracing through the diagram, I think you can convince yourself that what you get is the projection of the vector motion of the optical bench onto N3, plus the projection of the proof mass noise onto N3, and then you've got the velocity of the optical bench on the, well, sorry, this is the distant optical bench, and this is the local optical bench. And similarly, you can trace through and see that what the metrology data give you. They give you the difference in clocks on two different optical benches, plus the a component due to the relative velocity of the optical benches and the little proof masses.
So your capital V's are optical bench.
Capital V are optical bench velocities, little v's are proof mass velocities. Thank you. Yeah, I forgot to say that. Right. And the notation in things that you'll see later is that if you have a time delay of a distance L3 divided by the speed of light, that's indicated by a comma and then the arm length. So a delay of the time delay in arm length 3 gives you a comma 3, and that just makes the notation a little bit more compact. There's nothing more profound to it than that. Okay. If the arm lengths are unequal, but not time varying, and the lasers have the same frequency, you can form many linear combinations. This is the one that we thought of first, that's why it's called alpha, which consists of a sum of these little Doppler shifted time series, the Yij's, offset in time according to the arm lengths, plus a linear combination of the metrology data. And you can just brutally plug in and demonstrate that the clocks cancel and the capital V's cancel, the optical bench motions cancel exactly in the approximation that the center frequencies are the same of the lasers, and there's no Doppler shift due to the relative motion of the spacecraft. So that cancels those noises, but it doesn't cancel the other noises. It doesn't cancel, for example, the proof mass noises, but it modulates them. So the little v's here are the proof masses on spacecraft or optical bench 2, 3 star, 3, 1 star, 1, and 2 star. So the alpha combination contribute all of the optical bench, all of the proof masses in all of the spacecraft contribute to noise in alpha. And you can see how the structure is going. Now you have situations, if you just look at if you consider V2, the little proof mass noise in optical bench 2, then you see the structure. It's V2, 3 minus V2, 1, 2. So this is the difference of these processes by one arm length difference, assuming the arm lengths are all about the same. So that means you're going to get, in terms of trying to evaluate the Fourier transform, later on we'll want to evaluate Fourier transforms of things to get spectra, so I'm going to just bore you. I'm sorry to do this, but I'm going to remind you that if you have a linear system with an input and an output, you can characterize that system by a time domain transfer function. So the output is the convolution of the input and the transfer function. But if the transfer function is just a pure time shift, which is going to occur in many of these things that I'm going to show you in the rest of the talk, then all you get is that the Fourier transform of the output is just the Fourier transform of the input multiplied by a complex exponential. So if you take the difference of the data at time now minus the time elsewhere, in the Fourier transform domain, you're going to get a delta function from the first one, and you're going to get a delta function times e to the I 2 pi f offset in the other one. You take that complex number, square it, and that's going to give you the spectral modulation of that particular noise source. And that's all I'm going to do in the next few minutes is to walk through two examples to show how you can calculate, if you were so inclined, the spectra of the noises of any of these things in a very simple way. Okay, alpha used all six of the lengths. The two that I want to talk about in some detail, because they're favorites of people, are the unequal arm Michelson, which uses only these 4 lengths, and one which has come to be called the symmetrical Sagnac, which uses all 6 lengths in a very symmetrical way and has some nice properties for understanding the noise in the instrument. Okay, so sorry about this view graph, but what's the point of this view graph? The point of this view graph is that the unequal arm Michelsons are given by this equation. So you take, they only depend on those 4 lengths that I showed you in the previous view graph, but with various offsets, the comma 322 and so forth.
So remind me, commas mean what?
Comma means delay by, so comma 322 right here means you take the y32 of t, a time series, and you offset it by the time delay in arm 3 and 2 times the arm delay in arm 2 twice.
So it's t minus L3 minus 2L2?
Exactly. And you can see that in the structure down here below, which is the gravity wave. So this is the definition. This cancels the optical bench and the laser. If you then just plug in using Hugo's equation to evaluate what the gravity wave response after doing all this differencing is, you get 8 events. If there were a gravity wave, impulsive gravity wave, there would be 8 events in the time series. And this is exactly what we're seeing. So these are the time delays that you talked about, Bonnie. So this is just these are the, so there's L3 minus 2L2. That's associated with that event.
So those are delays at least as long as
The worst ones that I'm aware of are 4 delays, so they're of order a minute, yes. These are 3 delays here, so not bad in some sense. So you have to turn the thing on and the data don't become valid until a minute later.
We'll eventually know how exactly that needs to be managed.
Well, I'll allude to that, but the short answer is that you need to time align these things to about 30 meters, which is 100 nanoseconds or so. That doesn't strike me as a hard problem. Yeah.
Now, what about when your timing data is going to come at kind of 1 second weeks or something? So those delays will fall between.
Right. Okay. So let me just. I'll blather on. I haven't thought about this carefully, but it seems to me like what happens is that you have synchronized clocks on these things, and you're sampling pretty darn fast. Yeah, 10 megahertz is not bad. But the point is, and I'll talk. The sampling is going to be a problem. I think that's one of the practical problems I want to talk about at the end. But for the moment, putting that aside, then you just got to keep track of these pointers about which sample you really want to. You're going to take 10 million samples per second, but you're only going to pass a few of them over the telemetry link to actually be used. And so you got to have the clock synchronized, but you got to do that anyway for other reasons, I think. But that's how I would do it, I think, if I were tasked with the problem. And these are really, by RF standards, these are low rates. These are not a problem.
Which is only 30 photons in 100 nanoseconds.
No, but your integration time is not equal to your sample time. Your integration time is going to be more like a minute, more like a second. Yeah, so those two are not related. You're going to have to band limit the signal first, probably to 1. Yeah, okay, fine.
It sounds like full details haven't really been worked out, or you just kind of think that it's.
Oh, I think the details in terms of whether it will work mathematically have.
Oh yeah, mathematically. The implementation.
The implementation, I'm close enough to friends who are engineers to have talked with them in the hall, and I have not talked to the spacecraft engineers, however. But this business of keeping track of which sample you need, I think, is not a real problem. But I will. Okay, I'll jump to what I think is going to be a problem later on, and that is that you have to cancel 140 dB of noise. So the rule of thumb is you get 6 dB for every bit of A to D conversion you get. So you're going to need of order of 30 or so bit A to D converter to make sure you've got enough. That's probably not a problem. But you've got to have the gains of these things matched fairly carefully around the array so that you don't inadvertently have one that's slightly different than the other, and so it'll screw up when you do these differences. You're doing differences of big numbers to get small numbers. And that's something that I think is a research problem. I don't know if anybody in the LISA project is worrying about that, but that's a disadvantage of not combining the data optically first and then sampling it.
And quantization noise is not a problem?
Well, quantization, I mean, you you can buy 24-bit audio A to D converters that are very good, operating sort of at a kilohertz. So if you want to, yes, if you want 1 hertz, I would think that going from 24 bits at a kilohertz to say 30 bits at a hertz, I would think that would not fundamentally be a problem. I'm worried a little bit more about matching the gains of these A to D converters around the network, around the array of data. So that's a part. I think that's a problem that needs to be looked at.
I'm wondering about the transfer function. How do you get the transfer function of the
The question is, how do you get the transfer function when Lisa's in space?
Yeah, do you have any calibration facility?
I'm going to actually talk about how you can do that. The form of the transfer function I think is known, because I think these equations are okay. To actually decide whether Lisa is behaving as you predicted based on the pre-launch thing, there's a way to do that, and that involves this symmetrical Sagnac combination, and I will talk about that in about 3 minutes. So let me just quickly run through the what's the point here? The point here is that you can write down transfer functions, time domain transfer functions for the proof masses in the unequal Michelson and for the shot noise. And the bottom line is that if the arms are equal, then you have this kind of spectral modulation. So you have the spectrum of the proof mass, which is one of the inevitable things that Bonnie talked about, that there's just inevitable noise associated with the proof mass. And once you form these combinations by time offsetting and shifting and multiplying, then a consequence of that is to introduce in the spectral domain these e to the I 2 pi time shifts. When you just plug in the equations and take the modulus squared of those things, these are the functions which would then modulate the raw proof mass spectrum, and similarly the raw optical path spectrum. So for the purposes of this graph, yeah, this is L1 equals L2 for this equation, right? The general equations, I'm going to show you some plots which don't assume that, but it's much easier to write these things down if they're equal arm length. In fact, if you hand the problem to Mathematica and tell it the arm lengths aren't equal, Mathematica quote unquote simplifies these things in very funny ways, and it really looks ugly. So your question was, how do you tell about on orbit? One way is to use all 6 links in the symmetrical configuration. Symmetrical configuration is this one, zeta, which has the property that each of the Yij's is used exactly once, and each is lagged by exactly 1 lag. All of the others had either no lags or 1 lag or 2 lags. This one is symmetrical in the sense that each one is lagged only by 1 arm length delay. It has a 6-pulse response in gravity waves, but it has this neat property that if the arm lengths are equal, then it is relatively insensitive to gravity waves, and I'll show you some plots in just a second. So what you get here is a situation where you see all of the noise because each of the Yij's enters. You see all of the noise in the array, but none of the signal. So you have a situation where you're allowed, by forming, say, 2 time series, you form the unequal arm Michelson X and the zeta thing. One shows you signal plus noise, and one shows you noise only. So it's like Dickey switching. And you can, by looking at the noise in zeta, you can decide whether the actual on-orbit data are consistent with your pre-launch calibration or not. And further, you can tell whether the spectra, like all real random processes, are non-stationary, whether they're changing with time. So I think a very powerful capability is to be able to form this particular time series to evaluate how the array is going without having to worry about all those pesky gravity waves that you're getting in there.
So this is Sagnac combination?
This is the so-called, yeah, although Peter Bender likes to call it the symmetrized Sagnac, but yes.
And presumably the cancellation is only at low frequencies.
Yeah, let me show you, okay, let me just skip. Okay, so before I address Kip's question about the cancellation at low frequencies, which of course is exactly right, let me just say that there are, in addition to the unequal arm Michelson and the Sagnac and the alpha beta gammas, which I talked about here, there are 3 others which involve only 4 of the 6 links. So you can afford to lose any 2 links and you still have an experiment. You don't have the experiment you like necessarily because you don't have zeta, but you can form situations where you listen only at spacecraft 1 with these 2, don't transmit, monitor, or you transmit only, which is like the beacon, or the relay which goes around. And all of these, the sort of nitpicking details are in that white paper or in any of the references well, in the later references, at least, of the list that I showed at the beginning. So just linear combinations are not fundamentally any different in structure than what you've already seen. So, and I should also comment that only 3, the function space for canceling the laser noise is 3-dimensional. You don't get, X, Y, and Z are not independent of alpha, beta, gamma, and are not independent of PQR, but there are various algebraic relationships between the 2. So these things are all developed in the papers too, but there's only 3 independent ways to do it. So this is meant to be a summary before I talked about the sensitivity, and that is that I've already mentioned that you treat LISA symmetrically, that the function space is 3-dimensional, that there's a combination zeta which is insensitive, as Kip says, at low frequencies to gravity waves, but sensitive to the noise, and that it's possible to form many of these things, in principle, as many as you want, simultaneously, if you keep track of, as Bonnie pointed out, you keep track of the time so you can pick off the signal when you need it. So here's the application that I'm going to talk about for the remaining, most of the remaining part of the talk, and that is sensitivity calculations. The conventional LISA situation is to consider one class of source, periodic waves, for the purposes of sensitivity calculations, and that is the strength of a periodic wave you would need averaged over sky and over polarization to give you SNR equals 5 and a bandwidth of 1 cycle per year. So
if you look at the various noise curves that are published, this is what is usually published. That's not what I generally use. I use a spectral density.
Right.
Usually use spectral density from the things I show in the class. This is what.
Right. In fact, there are many advantages to using spectral density. I'm not particularly. This is one class of source and one way of thinking about it. Whereas with the spectral densities, you can apply what you think the waveforms are, and then do your own thing.